Okay, guys, let's start. So today we're going to cover the approximate reinforcement learning, and if you remember last time, we have been doing the MDP, and hopefully you have covered Monte Carlo methods at home. So in order to open this notebook, I suggest you going. Okay, let's do it in another window. Okay, so here, and there is a subdirectory reinforcement learning number 2, and here you have day 2 solutions new and day 2 task new. So choose whatever you want. I have chosen the task notebook. Okay, so getting back to approximate reinforcement learning, this mainly correlates with the lecture number 2 by Professor Whiteson, but also in the beginning we are going to cover the tabular Q-learning algorithm. So firstly, I don't know, I think you can see it in, I'm sorry if the picture is too big to fit in the screen. But today we're going to work with a very interesting environment, which is called Mountain Car. This environment is available in OpenAI Gym. And basically the main idea of this environment is so that you're using, so basically you can see there is a car and there is a hill, right? And then there is a goal on the hill. So basically the car wants to get to the goal, but unfortunately the engine is not working properly, and so all you can do is to push a little bit to the left, push a little bit to the right, and basically if you know physics or like you have common sense, you are going to kind of swing back and forth until you gain the momentum and go on top of the hill and reach your goal. But as you can see, right, this is a little bit different from what we covered during the last tutorial, because here we actually have the state space firstly represented by 2 values. The first value will be the position of our car along the x-axis, and the second one will be the velocity of the car at each position, right? At each time step, this will be correct. So here you can see that the first state goes from -0 or -1.2 until 0.6, again continuous, and the velocity goes from -0.07 to 0.07. And the actions are basically the action space is discrete, thank God. There will be, you're going to be pushing left, so basically this represents some force with which you push, the direction of the force that you are going to be pushing your car, and so push left is basically some, in a way, deacceleration, so you are going to go this way, and pushing forward is acceleration, so you are going to be pushing along the x-axis. And you have also an option of not pushing at all, which is 0. So what about the reward function? The reward function is for hitting the goal, it's 100. But for taking each step, for taking any action at any particular state, you're going to have, and this is actually like something that, I don't know, something new that I found, because I always, and every tutorial that I have seen has considered the reward being -1, but for some reason I saw that in OpenAI Gym documentation and like their GitHub, their implementation of Mountain Car, there is -0.1 times A, so A is an action, you see, like -1, 0, and 1. So nevertheless, I mean, If we're following some classical tutorials, it will be -1. If we're not following any classical tutorials and try to do like OpenAI gym way, it seems that it's -0.1 times action. So okay, so this is our environment. Again, the main problem here is, apart from that this task is a little bit harder than any grid world general MDP that we have been trying to do last time, this is a harder task. It needs a lot more like exploration to do, but also the state space is continuous and it's represented by two values. Okay, so what we can do with it, right? And here comes a very powerful and so here is like the make environment function, which basically is like OpenAI gym make, but we're going to do it longer. Yeah, we're just going to make it longer with the number of maximum episodes, maximum of time steps during an episode will be 1000. So yeah, we're going to use Q-learning. And this is actually a very, I would say, popular, very hands-on method. And this is actually, if before last tutorial, we will be doing like toy problems, we've been like playing and, you know, with dynamic programming and like the like fully observable MDP, like it's not really applicable to real life problems. Here, this is actually that you can try to apply to your own problems at work, in research, and yeah, Q-learning, even now, even though it was like, you know, invented and published, the article was published, I think, in the 90s, you know, it still is relevant and it still is widely used. So, tabular Q-learning is exactly how it sounds. We're going to create a table. In our case, it will be not a table, but a three-dimensional matrix. And we're going to first, right, fill this table with some initial values. You can like be smart about it and try to initialize it in some smart way, right? You can put zeros, you can put like whatever, because it's usually is going to converge. So, and then we are going to hopefully go through all state and action, you know, space. So at each state, we are going to try to take each action. And according to this formula, we're going to update each Q value. And in the end, our policy will be for each state, maximizing, again, the value which will represent the action that we're going to take. So the maximum Q value at each state is going to be our action, which is the argmax is going to be our action. So what I also want to like give you is maybe, because this is very relatively easy, right? We're going to do it right now, but what is this formula? What does it represent? So we're going to update our Q function. So each time we visit each state and try each action, we're going to update our Q function, and we're going to update it by this term. And if you look at the red colored term, this is like the reward, plus the discounted maximum, so basically plus the discounted delayed reward, right, we're going to achieve. So we're going to look at the next state and the next action, and this next state and next action actually will unfold itself, right? Unfold itself into next states and next states and next, and we'll look into the future, and we will see the expected delayed reward, right? So this is like temporal difference term. And what is here, right? This is, we are going to how do you say it? Okay, that we are going to minus the Q value, the initial Q value in this state, in this action, and because we're all machine learners, right? We're all data scientists. We can look at this as if this is our target. This is our like ideal, let's say, something that, you know, something that if we take this state, if we take this action at this state, and we look into the future and we see how much, you know, how good our choice is compared to the one that we already have. So we will be very unhappy, right, if this will be negative, meaning that, you know, we we will need to decrease the Q value. If this will be positive, it means that we are progressing, right? That this action at this stage actually, you know, at this time step, we have improved our Q value at this state with this action. So I hope I described it somewhat intuitively to you. And so here is the tabular Q-learning algorithm. So again, we're going to use the policy that we've been deriving from the Q function, Q value that we have, right, from the Q table. We're going to be doing it epsilon greedily. You won't see it, you know, here, but I can assure you that we're doing it epsilon greedily. Then we're going to take this action that we have chosen, observe the rewards, and observe the next state, and with this we're going to update our Q value. So this is the Q-learner is some class that represents an agent. So you can look into rel to utils if you want to see the this base classes. However, you know, in Q-learning there is nothing interesting. It's just a layout of all of the classes that we are going to modify, basically. So again, we are here initializing our learning rate. So here it will be alpha. The number, important thing that I forgot to mention. Yeah, we have a continuous, as I said to you, I think 2 or 3 times already, that we have continuous state space, right? So what can we do about it? You can ask me. And I can tell you, let's discretize it. Let's try to have, right, this range from minus 1.2 till 0.6, and let's try to divide it into 40, in our case, into 40 states, right? If our like continuous state is close to the state, we're going to just if some continuous state kind of falls into this 40 discretization, we're going to consider it, you know, belonging to this discretization class, right? So pretty easy. This is how you can, and this is how we are going to be dealing with the continuous state space problem. Okay, so here we actually define the Q table, right? So this is going to be number of states. So number of states, because we have, again, remember, like state space is velocity plus position, velocity and position, and on the third dimension we will have the number of actions, and this is already discrete, so we don't need to worry at all. Okay, so state to index does exactly what I told you to do. So we have some states, we have a discretized state space, we put this state into the state to index function, and this will give us the 2 indices that will represent the first 2 like indices of our matrix that represent the state space. Okay, right. So here I want to try to make to actually implement this tabular Q-learning. What we're going to be doing is basically this function, right? This function, and we're going to update the Q values. So firstly, so that it won't be like extremely big, I want to implement this TD error, temporal difference error. Yeah, so this is called an error. I already told you why intuitively this is an error. So because this is a target and this is like our current value of Q value, it's action value function. So let's try to do it together. Okay, so TD error, it's reward, right? We have reward plus. Here I also advise you, because of the implementation details, we are going to be doing we're going to be tracking the done flag, and if we are already done, we're not going, if we are done here and we will come to update, we're not going to update our Q value anymore. So yeah, so if we terminated, if we have terminated our state, we're just going to add our reward. Okay, so not done. Times gamma, right? What? Bigger. Okay, yeah, sure. One. This is command 0 is command plus. Okay. Oi. Is this okay? I hope it is. Okay. So let's do the self gamma times. What else do we have there? We have maximum of Q. So NP max of NP max of we have Q table, right, as self Q table, and we're going to take the values. Well, actually, the indices. So probably this is smarter to be, implemented like this, just for clearance. So A next, right? A next. B next. So this is going to be our future Q value, right? Maximized Q value, so our target. And then we're going to be right? So we're going to do minus Q table, current state, our current states, and our current action. So, okay, I think this is okay. Yeah, thank you so much. Okay, and next we're going to be updating our Q table. So it's going to be A, B, action, and it is going to be equal to self Q table, A, right, B, action plus self alpha learn rate. We have it as learn. We just have, I think, rate no, self. Times our TD error times our TD error. I think that's probably it. And okay, so I also, for your kind of consideration, I also have put the plotting. So we are not going to run the OpenAI Gym environment. Unfortunately, I suggest, because you already know how to implement OpenAI Gym functions from the last tutorial, I suggest for you to do it yourself at home if you're interested. But now we're just going to be looking at plots and our learning plots, and we're going to analyze them and think about what should we do next. So here are these functions. The results that we're going to plot. So here we're going to run the experiment. Hopefully nothing will crash. Oh, yes, good. Okay, so yeah, this is probably going to take some time. But you can see right here, you will see it on the plot also, but you can see that gradually our reward becomes bigger. Well, sometimes not, yeah, sometimes it oscillates, but it's fine, it's okay. We're running it for 1,000 episodes. Each episode has, as you remember, 1,000 time steps inside of it. And let's plot what we got. Yeah. Right. If you don't mind, I will probably do like this, just so that we get everything into the picture. So, okay, what does this plot tells us? Does this plot tell us? So basically, this is the number of episodes that we have been running, and this is the reward of our episodes. So we are going to sum all of the rewards for all of the time steps, right? And this sum is going to be plotted here. And as we can see that this sum, right, is going upwards, and it actually converged to something, and it's kind of more stable now. It's not really growing, or not as much, which is a good thing. So here you can see that oscillation that we had over here. And what are these plots? So here we have plotted the value function, and again, as you remember, our state space is represented by the car velocity and by the car position on the x-axis. And so here the value function, basically the blue color is the the lesser, smaller value function values, okay? And the red ones, the redder they become, but I mean, you can see it here. The redder they become, the bigger the values of the value function become. And so what can we say here? That very logically, our tabular Q-learning has distinguished that if we get, so this is probably, right, the place where the bottom of the hill is. So, and here, of course, its value is minimal, right? Because the algorithm understands that this is like the place where there is like the, you have to do lots of actions, its value is very small. So but if we go, for example, toward the hill, right, if we're on the slope of the hill, the values become continuously increase, because the expected reward is also increasing. We are very close to our goal, and we are doing the right actions to reach our goal. And here is the greedy policy with respect to this value function. So basically, these are, green color, or green color is the we don't do anything. Red color is we go forward, and blue color we go, we deaccelerate. So, and what is this spiral, right? This spiral actually represents to us that our car should go, if, again, I think all of you are familiar with physics, and this means that, in order to reach our goal, right, we need to go back and forth in terms of like the velocity, right, in terms of the position. And so represented in a 2D space, this is going to be like this kind of spiral thing. And we see that eventually it reaches its goal. However, we still want, it's like a little note for us that we still want, for this amount of spiral circles, right? Circles in the spiral, we want to do the least amount. We want, the least amount of actions to be done, because all of our actions get small, get minus some reward, -1, let's say, because all of our actions get -1. We want to do the least amount of actions we can possibly do to get to the hilltop. Yeah, we have 15 minutes, so I hope, this is just a heads up about what's to come. So here there are implemented like approximate Q-learning that you have already learned on during the your second lecture. There are also implemented a double Q-learning algorithm, and there are also like a very exciting thing. Finally, in neural networks, deep Q network, and it's in the very end. So if you are interested and we don't make it in time, I suppose that you cover it yourself. I hope it's not too hard for you. Yeah. But coming back to the tabular Q-learning, of course, this is a cool method. It's very intuitive. It's very easy to understand. It kind of goes directly from what we have learned when we were learning MDPs, right? So the iterative processes that, we can improve Q. We can improve Q, and in finite time steps, we can get optimal values. Moreover, we represent our Q function as a table, right? Which is much more intuitive than just, a function, and much more easier for us to pick for each state. It's much easier to pick an action this way. However, and yeah, also it is like it's actually very stable. Don't mind this, it will get worse. It's usually like if you have a not very hard problem and not a problem with a lot of states and not very hard rewards, you will get a good convergence. You will get a good policy which is close to optimal. However, you may tell me that, Nina, let's imagine that we have a state that is described by not 2 values, but let's say 3 values, 4 values, whatever number of values. So our matrix is growing and growing and growing, and it's become, on top of that, it will be harder for us to fill in this matrix for each of the states and each of the actions, right? It will be like, it will take longer, right? It's like the matrix will grow and grow and grow. Maybe sometime it won't even fit into our memory. This is not very convenient if we are talking about like big world, like grown-up problems. Like, let's say we want to teach a robot, right, how to walk, and this robot has a lot of joints, and these joints, in order to walk, the robot needs some torques, and we need to track the angles, the positions, whatever, like a lot of different things. For us, to learn an optimal policy, that's not a it's actually not very simple task. Believe me, to find a good representation of the state space that will give you good results. So can we, let's say, approximate our Q-learning function with some other function? This will, it will save us a lot, it will save us from doing all of this matrix, Q table, and so on and so forth. And actually, we can do this. And let's say that we want to approximate our Q-learning function with some other function, right? So here, let's say the Q star SA is our, of course, optimal function. If you are like, sometimes we can even approximate some random, some policy function also. And we are going to approximate it with some Q function parameterized by theta. And so I will now introduce to you the semi-gradient. Yeah, just because it's easier for me, but the exercise 2A will not cover exactly this. So just as a general layout of our problem. So let's say we have some objective function, let's consider it, which is actually this TD, like very similar to TD error that we have seen before. Here, and so let's try, here we use the bootstrapping, and let's try to find theta, right? So we want, of course, in some possible future to make this as close to 0 as possible, this subjective function. So let's try to find, the gradient of the objective function with respect to theta, and using like gradient descent, make some small steps in the direction of optimal weights and our function approximation that will give us an optimal Q function. So, but here comes the notion of semi-gradient, which is the name actually was invented and was introduced like many of the things in reinforcement learning by Richard Sutton. And why semi-gradient? So here we are going to fix this theta. We are not going to optimize this term, as you can see, by theta. From what I know, some people tried to, do not semi-gradients but full gradients, but they didn't succeed much. And yeah, you can try it yourself, but from what I know, it's not really a good solution, and it won't lead to like anything good for us. So let's do the classical way, as smart reinforcement learning people tell us to do it. So let's use semi-gradient. However, for now, forget it, or like, yeah, forget this thing, or remember this thing, but in the back of your mind. And for now, I want for us to look at this formula. So let's consider, as we said, we want to approximate our Q-learning with linear functions. So let's consider that our Q function is a linear combination of some basis functions phi, and it has some weights. And in the same fashion, we are going to find the gradient with respect to v, like here it is. Here, like 1 divided by 2 is alpha, or will be introduced in alpha. So just so that this 2 will, become 1. So so this is basically, as you can see here, we don't use the v because of this linear combination. because of the linear combination. Let's try to find, and here, right, let's try to implement this, but here I have introduced to you two basis functions that we can try to use for this as phi here. So one basis function is a one-hot encoding function. So basically, what this function does is we have some state, which is represented by two values. We are going to feed this state to our one-hot function, and this function is going to return to us, let's say, a matrix filled with zeros. However, at the point, at the cross of the state, the first part of our state and the second part of our state, there is going to be 1. So this is like 0, 0, 1 matrix. Very easy, right? Very intuitive. And we're going to do the radial basis functions. And here the logic is mostly the same. However, right, as radial function implies, the state, the cross section between like the state, the first term of the state and the second term of the state is going to be 1, and then it's going to radially, decrease. The values are going to radially decrease from this point in the matrix. So let's try to put this phi inside this our algorithm. Let's try to implement this. And so here I have already done for you like the linear Q-learner agent, right? And so let's try to implement this. So here again I propose to do TD error separately, and because it's completely the same as in the previous section, let's just copy it. Right? Is it the same? It's not the same, but we will see why. Because we're not using a matrix now, we're going to use a function now. Different thing. Okay. So again, reward, the flag, the gamma. However, here we're going to use the Q value sub function from the next state. Right? Right. And we're going to use the select values. That should stay. Okay, and here we are saving the weights in a table. So we're actually going to do the action like this, right? I think that's right. I don't know what I'm doing. Self-weight action, right, plus self-learn rate times TD error times TD error and times the basis, our basis function. So it's self basis from state. I think that's right. I hope at least. Huh? One second. Yeah. What again? Where I have made a mistake. Self weights, right? So self weights. Yeah, self weights. Try it. No. Basis functions is not defined. Ага. Так. Okay. Is it working? No, it's not working. Name key values is not so I was right the first time. Right? Eh? Something's not right. Okay. Oh, we're late, so let me just do a bad thing to here. Where? Okay. Here. Yeah, completely forgot about that. So here we're just going to be trying the one hot encoding basis function, right? So it's going to train for some time again. And I hope between the break we will see what we will get and how it will look like. So again, we see very bad at first, then better, and while it kind of works itself out, I will probably tell you a little bit about what you can do at home. So I also propose for you to do the one with RBF basis function. So yeah, so you can try it out yourself, see how especially I want you to look at how the value function, the heat map, right, this thing is going to be different in one hot setting and in RBF setting. Okay. Yeah, it trained. Let's have a look. Yeah. See. So here we actually we have plotted the tabular Q function that we have found, and the linear approximation was one hot encoding, and we can see that even the value functions looks somewhat different, but again, see the number of circles in the spiral. So although we get this, better reward, still it seems to be very suboptimal. And also, like, this oscillates a lot, right? And if you restart and try to, try different time, try to experiment with it, you will see that, sometimes it's basically, drops and, and the oscillation can be extremely big. So for ABF basis case, I propose for you to do the same thing. In here, there is some stabilization of approximate Q-learning using target networks. So this is actually when we are going to be doing what I told you about here. So basically, we are going to be having some target Q, right? Q value, target approximation, which is going to be somehow you will see here that is going to, and this at this step, this is an easier explanation that at this stage of update, this and this parameter are not going to be the same, and this is why, right, the semi-gradient comes in the picture, right, and this is why we don't need to take the gradient from there. And so here you, or you can look at the solution. I mean, it's not completely different apart from the fact that we also define the target Q values and the update of this, of the parameter of the target Q values. Right, then the double Q-learning, I have found this example which shows us why, you know, real, general Q-learning is not, working sometimes. And this is like an example where we have the gray states are the terminal states, and and the rewards for going right is going to be 0, for going left is going to be 0, but as soon as we get this to state B, we have a normal distribution of rewards with the mean of minus 0.5 and variance 1. So you can see, because our, here, if we consider like the random, right, random variables that are picked according to this normal distribution, we can see why our Q-learning algorithm can actually give us worse results, right? Why our algorithm, instead of going to the right, where it seems much safer and where you get 0 always, why it will try to go to the left, and get in, if we do a lot of time steps and experiments, why, the mean here will be minus 0.5, but because here we'll have a positive reward, right? 0.5 was plus. Why this is going, why Q-learning is going to be choosing this side. And so for this, to cope with this situation, was created the double Q-learning that Professor told you about. This is some reminder, this is some algorithm that you, I hope, are going to implement. And actually I haven't done anything here because I think it can be confusing in my code, where is QB and where's the QA, because you are basically in double Q-learning, you have 2 Q-learning functions that we are going to, and each of which you are going to use to update another one. Okay, so yeah, again, deep Q-learning reads a very fundamental article about DQN, where it was first introduced, which is basically gave the start of deep reinforcement learning. And also suppose for you to do this. Try to play with the architectures, try to see what works best, implement it, just run it, see the results you get. And that's it probably for me. Thank you so much for your attention.